Meet Robert, a highly intelligent companion robot that loves to tell us what he sees, and he loves to play with mazes. He can sometimes be in his own world and require a little bit of waking up. Yup, that's what we mean. Let's now meet the engineering team of the amazing robot.
We begin our journey with the architecture. We have a Raspberry Pi, a STM32 connected via UART, a laptop connected over Wi-Fi, and an Android device connected through Bluetooth. The Raspberry Pi connects the various devices through the use of 3 different socket servers. Firstly, the Bluetooth socket server. It has a predefined 30-character padded buffer which will handle the majority of the required communication packets. For data that is larger than 30 characters, we utilize a simple pre-flight negotiation to dynamically adjust the received buffer size. The sending and receiving of data is done on separate threads to ensure non-blocking I/O operations. Next, we have a HTTP server. The server facilitates video streaming from the Raspberry Pi to an external laptop in the Pi's LAN for image recognition. It also has multiple endpoints which enables two-way communication between the server and detection client. Lastly, we have a UART socket server with a fixed 5-character buffer which allows us to communicate and issue movement commands to the robot itself.
The STM controller governs the movements of the robots. For the task to succeed, we need to ensure the robot's movement is precise and accurate. The Hall encoders were used to ensure that the robot moves the exact distance as instructed by the algorithm. A PID controller is used to ensure that both left and right wheels are moving at the same speed. To minimize the turning radius of the car, a 3-point turn is implemented to ensure that the turns are in place, which allows for better maneuvers to avoid the obstacles.
For Android design, we kept our UI simple and intuitive, focusing on a unique color palette and complementary color pairings that give off a bright and energetic feel. Before development, we constructed a hi-fi prototype to visualize how our app is going to be like. This has helped us identify key components and displayed all of them on the main page to minimize the number of user clicks and interactions.
We also allocated sufficient sizes for each Android components so that the components are not cramped together and are sufficiently spaced apart from one another. Another feature of our app is to display the obstacle's coordinates in the position component, allowing us to plot the obstacle faster and more accurately.
For image recognition, we are using RoboFlow to label every single photo and also use data augmentations to ensure the usage in different scenarios. With this, we are able to achieve around 16,000 photos. We started training and testing with YOLO V5M, which is the best model architecture for RPi devices. We are able to achieve a high accuracy of the correct image after various adjustments. With the detected photo, we are able to use the image detections to calculate the distance and angle between our RPi and the object as well, which will be used by our algorithms to make calculations.
To traverse the grid efficiently, we first determine the optimal order of visiting the obstacles. Due to the small number of targets, we can easily test out all possible combinations and calculate which one requires the least distance to be travelled. We can now determine the fastest route to scan all images by finding the shortest path between consecutive pairs of obstacles as determined by the ordering. This is done using a modified A-star algorithm, which adds all the neighbouring nodes of a current position into a priority queue and selects the node with the least cost to further expand upon. The cost of a node is the weighted sum of the cost of reaching that node from the start and the approximate cost of reaching the goal state from that node.
For the run, we implemented a protocol in case no image is detected. During the protocol, the robot will move forward 1 block, do a scan, move backward 2 blocks, and then do another scan. It will stop and find the next path after the protocol is done or detected an image.